Everyone, Assalamualaikum and good day. Moving on in this particular session, we'll continue our discussions on Bode diagram method. But in this session, I will be discussing further about the example of how we can sketch the Bode diagram using the example given in this example ZEX 6.1, page 169 of the reference book I am referring to. All right, so we have this question, the problem here, sketch the Bode diagram of an electrical amplifier which has the open loop transfer function of GS equals to 200 divided by S plus 20. G of S equals to 200 divided by S plus 20. As you see this example, so this is the open loop transfer function lah. So you want to sketch the Bode diagram of this system. So basically what we do firstly is to start with converting this equation to the form that it is easier for us to identify or whether it is which type of the factors, whether it is constant factor, not constant factor. Of course, clearly this is not a constant factor. Whether it is a derivative factor or integral factor or the first order factor. Okay, so we rearrange this equation. G of S equals to 200 divided by S plus 20. Let's say we do it like this. Put the 20 outside of the, okay, so put the 20 outside and then we will get here 1 over 20 S plus 1. So that we can cancel it. So the numerator is 10 divided by 1 plus 0.05s. Meaning that this is the first order transfer function of 1 over 1 plus st, right? So now we can assign the factors. We can assign the factors so that we can use the log properties, right? Let's say we pecahkan, we split this function into G1 and G2. Let's say we pecahkan this function as G1 and G2, G1 times G2. See that G1 is K. G1 equals to 10 is like a G1 equals to K, right? Constant factor. For G2, it is 1 over 1 plus 0.05 S, which is, this is the, let's see, let me write here. This is the constant factor. Something like K. This is the first order system of 1 over 1 plus st. Okay, very similar function of the first order system of 1 over 1 plus st for G2. For G1, this is like a constant factor, but the gain here is 10, right? Not the gain, the constant factor, the factor here is 10, constant is 10. Now, once we do that, for this particular function here, we substitute S equals to J omega because we want to observe the magnitude and phase angle of the transfer function here as omega change from 0 to infinity. To substitute S equals to J omega for this function. So constant is no substitution. But for this one, we substitute S equals to J omega. So this is S equals to, that is S actually. Okay, so 1 over 1 plus 0.05 J omega for the G2. Okay, now we have factor G1. We calculate it one by one. Start from factor G1, the magnitude. Okay, so G1 equals to 10, then calculate the magnitude, the gain as usual. 20 log 10 lah. 20 log 10, this is K. K equals to 10, right? 20 log 10, then log 10 of 10, of course it is 1. This part is 1, meaning that we have G1 equals to 20 decibel. And then let's calculate the angle. The angle of G1, okay, arc tangent 0 over G1. Arc tangent 0 over G1. Because constant, G1 is constant factor 10 plus J omega, and this J omega part equals to 0. So arc tangent actually 0 divided by 10. Okay. So arc tangent 0 divided by 10, meaning that arc tangent 0 degree, arc tangent 0, which is 0 degree. Okay, finish for the factor G1. Moving on, we calculate for the factor G2, which is much more complicated for this one because it is a first order transfer function. So the magnitude of G2 is represented by 1 over 1 plus 0.05 j omega here. Then we can do the reciprocal. Okay, reciprocal of 1 plus 0.05 j omega is negative 20 log this part is actually the reciprocal of 1 plus 0.05 j omega. Okay, so we get the magnitude of the reciprocal of 1 plus 0.05 j omega here. Then we can consider the plot for low frequency range and high frequency range, and also the plot at the point at the corner frequency. So we will start with low frequency range. Let's say in this case, we consider the low frequency range of 0.05 omega smaller than 1. Low frequency range of S. Low frequency range of this. Okay. So at low frequency range of this, then we do the calculation. So for G2 at low frequency range of omega, negative 20 log square root of 1 square plus 0.05 omega square. Kita substitute ni. If this part is at low frequency range, meaning approaching 0 lah. If this part is at low frequency range, meaning that this part is approaching 0, so that we have square root of 1. Okay, we have the square root of 1, which is this part is dominated by 0, meaning that we can say that this part is 0 lah. Alright, so when omega is approaching 0 for low frequency range, we can say that this part will be 0. Okay, we can say that the square root of 0, because 0 is dominating for this function. All right, 0 is dominating for this function. In that this part is 0, then we get 0 decibel for the gain of G2 when at low frequency range. At low frequency range, 0 is dominating. All right. See, moving on. Next, we calculate for high frequency range. We calculate for high frequency, whether we want to calculate at the knee, at the corner frequency, or we can do it either. So I will start here. for the second one, calculate for high frequency range, which is at 0.05 omega is greater than 1. The magnitude is approximate to G2 equals to -20 log this part, okay, this part at high frequency range. Omega is high frequency, meaning that, for example, omega is equals to 1 million, okay, 10,000, for example, at high frequency range. All right, we can expect is that this part will be dominating. So this part will be dominated. So dominated by this part, like this one is small enough that we can neglect. So meaning that this part we can just assume that it is 0. Right? All right. So when omega is dominating, we could expect that it is remain at 0.05 omega, 0.05 omega. Similarly, we can expect this equation becomes -20 log 0.05 omega. Okay, this is small enough so that it becomes 0. So this function will be dominated by 0.05 omega at high frequency range. So we should expect this equation that we will use later to further calculate individually or at different points of omega. Let's say we will start to calculate this G2 at omega equals to 1 over 0.5. Why did we choose the 1 over 0.05? Because we want to cancel. When we replace omega equals to 1 over 0.05, so that we can cancel 0.05 here to become log 1. Log 1 is 0, meaning that G2 becomes 0 decibel. G2 becomes 0 decibel. That is the gain at omega equals to 1 over 0.05. Next, calculate omega equals to 10. Another decade. We start with 1, then 10, and then 100, and then 1,000, so and so forth. So next, start with calculate for the omega equals to 10 over 0.05. Then again 0.05 is cancelled, meaning that this part becomes log 10 of 10, natural log of 10. So that this part becomes 1. It is G2 equals to -20 decibel. Okay. Next. So once we calculated for different omega at 2 points here, at 1 over 0.05 and another, the point is 10 over 0.05, we get 0 decibel, and then next is -20 decibel. Then we should imagine that the next omega, if we substitute omega equals to 100 over 0.05, then we should expect the result of G2 becomes -40. So next, we determine the corner frequency. So once we determine the magnitude at that 2 points of omega there, next we determine the corner frequency. So to determine the corner frequency, back to the definition. Okay, back to the definition, which is the corner frequency is determined by equating low frequency magnitude with high frequency magnitude, and so for omega. Low frequency magnitude. This is low frequency magnitude part. This is high frequency magnitude. Make this to low frequency and high frequency magnitude equals, so that we can solve for omega. Then, so we solve for the omega here. Okay, we solve for the omega when omega is equals to 1 over 0.05. Okay, then we can cancel this to becomes log 1. Okay, to becomes log 1 this part. So that remain negative 20 kan. Remain negative 20. Alright. To further understand this is just a lot of shortcut here. Basically, negative 20 log 1 here. Log 1 means log 10, 1, right? So 10 power of 0 is 1. So here we have 10 to the power of 0. 10 to the power of 0 this part. Okay. Let me repeat. Let me repeat. Okay. For this particular equation, kena check betul-betul. Saya mungkin buat silap. Saya perlu ulang balik. Sorry for that. Let me repeat. For this particular equation, we equate low frequency magnitude to the high frequency magnitude here, represented by equation of negative 20 log 0.05 omega ni. Let's see, if we want to make this 0, suppose that we should make this equals to 1. Betul tak? Okay. So that this part becomes log 10 of 1. So that 1 is 10 power of 0. Right. So log 10 of log 1 lah, log 1. Log 1. So meaning that this part becomes 1. That is why this is 0.05 equals to 1. 0.05 omega equals to 1, so that we can solve for omega, which is 1 over 0.05. So here omega is 20 radian per second. Okay, omega is 20 radian per second for the corner frequency. Corner frequency. Next, we calculate the phase angle using phase angle equation of G2, which is negative arc tangent 0.05 omega. So this is G2, right? G2. 0.05 omega of G2 arc tangent. So here we sum up all of the angles, which is we have G1 and G2. Tadi kita split, kita pecahkan kepada dua. Okay, we have angle of G equals to angle of G1 plus angle of G2. So angle of G1 is 0 degree. Because it is a constant factor, right? So constant factor, dia punya angle is 0 degree. Mana dah? Angle of G1 is 0 degree plus angle of G2 using this expression, negative arc tangent 0.05 omega. So that the remaining function is only, for the angle is, so angle of G is negative arc tangent 0.05 omega. So we can further compute to estimate the points of the phase angle of G of S by substitute all of the values start from omega equals to 1, omega equals to 5, omega equals to 10, so and so forth. When we vary this frequency, what is the angle? using this equation, what is the angle when we vary omega? When we change omega ni, when we change the omega, so we can do it like this. The table is here. Okay, as the omega increasing from 1 to 200, all right, so the phase angle is changing. Okay, so we calculate it one by one. Substitute omega equals to 1, we get phase angle of -3 for the G. Next, substitute omega equals to 5, we get phase angle of -14. Further, we calculate it at, suppose that I've made another mistake. Sorry for that. Actually, the corner frequency is this one, yeah? Because we have already calculated this. The corner frequency here, we get 20 radian per second. This is the corner frequency. Okay, this is the corner frequency. Right? So at corner frequency 20 radian per second, we calculate the angle of -45 degrees. So and so far, when frequency is increasing up to 200, then we got the negatively increasing phase angles. Say that for calculating the corner frequency, just now we have done that. Actually, we have done that here. Omega is 20 radian per second. This is wrong. Let's say if I want to recalculate the corner frequency, where is the equation for corner frequency? -20 arctangent log corner frequency 20 radian per second. So angle G equals to negative arctangent 0.05 omega is 20 radian per second. Okay. So negative arctangent 0.05 times 20, because 20 is a corner frequency, then this one becomes 1 over 20. Okay, this one is 1 over 20. So arctangent 1, negative arctangent 1 of 1. So that this is 45 degree. Okay. So phase angle 45 degree at corner frequency omega equals to 20 radian per second. Then we do the plot. Finally, we do the plot. So we check one by one the points over the plot. So make sure that you clearly indicate the corner frequency here. Sorry. Yes, the line for corner frequency, which is 20 radian per second. Then we do the sketch. This is G1, the straight line, which is constant factor. Another G, which is G2 here, sorry. So G2, this is G2, this is G2, and total G is start from 20 constantly, and then straight line from a constant when the frequency increase, power gain or gain is constant at 20 decibel. At corner frequency, it turns downwards. All right, it turns downward till -20 here. All right. So we plot it as usual for this one as well, for the phase angle, start from 0 degree. Okay, 0 degree towards infinity. Okay, this is angle of G. So that is the way we can do, for example, of problem related to sketching the Bode diagram of an electrical amplifier which has the transfer function of G of S equals to 200 over S plus 20. This is, as we can see, that this is the problem related to sketching of Bode diagram for the what I call it, lupa dah, for the first order system transfer functions all. So I will finish it up to here. So I will finish up to here. I can prepare all the notes based on this example. Make sure that you prepare your own notes. Okay, so thank you.